All right, so Reyes here, and we continue with our robotic foundational model series. Last time we talked about the Pi0, the foundational models from physical intelligence. Yeah, we've introduced topics like VLA, basically combining VLM with an action expert, and talked about the flow matching. We went into details about flow matching, the code. We went through the code to simplify the formulas and the equations from the paper. Now, Groot builds on top of it. So Groot has a very similar architecture to the Pi0. There are like some minor differences, but it's more or less same. Like VLM, the action encoder part or the action transformer, and the flow matching. So let's talk about some differences between these two architectures. So one of them is the embodiment specific modules. So the modules that you see here for encoding the robot state or the action states and decoding the action state, they are separate or for every robot. That's important to note because this helps them dealing with the sim data and the synthetic data later in the paper. And that's actually the main part of this paper, the sim data and the sim data. Okay, another part is the VLM. So in Pi0, they use polygamma and then they fine tune it. So the whole transformer was like a unified transformer and was treated as a mixture of experts where you have different objective functions for fine tuning the VM polygamma and different objective function for the action encoder. However, in the crude paper, they don't fine tune the VLM. It's frozen. They only train the action expert from scratch. Root calls it System 1, and the VLM is called System 2. It's kind of analogy to how the brain works. So System 2 is more structured thinking, more organized thinking, and System 1 is basically just spontaneous thinking. Yeah. The other part is the action horizon. So in Pi0, they use the horizon as in 50, that is action chunking steps. So whenever they're generating action, they generate actions in a block of 50 steps. However, in the GR00T, I think 16 actions are generated together. Now, even in Pi0 paper, all in all of their long horizon tasks, they never used 50 as they never used like whole 50 action steps. As far as I could remember, it was I think 25 was the maximum steps they used before sending a new call to the model. So yeah, that's basically everything about the architecture. Like one small thing is that along with the flow matching laws, the paper, the GR00T paper also uses the object detection laws, so as the auxiliary laws. Now, why the auxiliary laws? I mean, this is pretty cool. Like normally in computer vision system, you add objective, you add auxiliary laws as a second objective, just to help your model learn the main action more specifically. Now let's talk about here. So in this case, what they're doing is they're asking the model to generate the bounding boxes for the main object that is being manipulated. So how it helps is by asking a model to generate the bounding boxes for the main object. It kind of learns to associate that object with the actions predicted. So it learns the spatial understanding between the object manipulated and the actions predicted. So yeah, and this is kind of this has been done in computer vision for some time. I first time heard about it was in the first AI lecture from Jeremy Howard. I think he was trying to do fish classification and he was then predicting the bounding boxes for the fish there, basically to help it understand like where to focus on for fish classification, where to focus in the image for fish classification. He also used that a lot in imitation learning, for example, self-driving cars, where if you want to predict just the driving angle and the value for accelerator or the brake, you ask still the model to segment the road, get the bounding boxes or 3D bounding boxes for the people around them and the pose around them. So the model automatically associates to learn the steering angle and um, the steering angle and acceleration and braking in association with this scene. All right, so that was basically everything around the architecture. Let's talk about now the main part, the main meaty part about the paper, that is the data generation and the synthetic data. Now, the first thing is how do they use the the human videos, human demonstration videos. So if you look at the data pyramid in the paper, they have like three parts here. One is the real robot data, one is the synthetic data, and one is basically a web data, the whole internet data. And one of them is human videos, basically human demonstration videos. You could think of it as like this video here, where they are extracting the DNA sample. Now it's a really good video. You have a person who is like, you have a very good top view and you have a person who is handling pipettes and samples. Now I cannot imagine like a better video for training robots. Like a slight problem here, however, is that everything what we have here is in the image coordinate. However, robots work in 3D space, like it's 3D, the robot coordinates. Now, if someone could find a way to work with this kind of data sets, wow, I mean, that would be pretty cool. And that kind of brings us back to the group paper. So they found a clever trick to work with the human demonstration videos or even like robot demonstration videos. And the way they do it is by training VKVAE. It's a variation of VKVAE. Yeah. So they use they sometimes get like very confused between VQVAE and how yeah. So they use the encoder of VKVAE and they train it to take the image at time step t, then image at time step t plus h in this case was 16, and for it then to predict the latent actions, that is latent vector of actions zt, then you use again the image at time step t and the latent action to reconstruct the future image at time step t plus h. Okay, so you have an encoder which takes two images, image 1 and image 1 plus h. Then it generates a latent variable, and then you have reconstructing the the 1 plus h image using latent actions and the initial image. So what the model learns is what kind of actions it need to take to reach from the initial image to the final image or to the second image, which is image plus the action time steps it takes to get there. Now, it is not exactly learning the exact actions, but it's learning the higher level actions. For example, you can call it something like move the arm to the right, or sorry, move the right arm to the left, or move the right arm to the right, or pick up the object from the left, drop the object to the right. These are like more high level actions, which are kind of common across all the embodiments of robots and also for the humans. So they give example here. So once again, if I wasn't clear, they do not predict the direct action labels, but they predict the high level description of the action, what is happening in the image. Like how do you go from image A to image A plus 16 in this case? And how, like, what action do you need to take? Okay, you need to move the arm to the left side. Okay, you need to drop the object into the box. And then they use these latent actions as the pseudo labels for training the GR00T policy. Now that is the one part of it. Like very cool if you can use something like that to take like ton of demonstration, first person view data set for robotic training. Now the second one also found like very cool. Before we talk about the second one, let's just talk about data augmentation, right? So in around 2015, 2016, or like around that time, this was our state of art data augmentation. You basically flipped the image, you zoomed in, you zoomed out, you padded the image, you added like some pixels here and there, you blocked out some part of the image to make sure that the models don't overfit. And then around 2023, Google came out with Rosie. So they did the inpainting of images to generate inpainting data set for robots, like this one here. And that was already pretty cool. You also have this new paper called Robo Engine. They do something similar for creating physics-based or physics-grounded augmentation for images. And what NVIDIA did was, okay, you had manipulating images without inpainting, so like very, very classical manipulation of image, rotate, turn, zoom in, zoom out, scale. Then you had inpainting of the image. Then you had consistent inpainting of the images to make a video. And then NVIDIA went a step further and did like complete generation of the video. So What they do is they take the existing robotic data set, right? They have 88 hours of robotic data set, which is like a real life data set that a real life data set of teleoperated robots. Now, using the data set, they fine tune an image to video model and then generate around 5 to 10 seconds videos of given the initial frame. So something like this here. This is the initial frame, and then ask it, prompt it to generate, say, hey, use the right hand to pick up the cucumber in the basket. And this is the generated frames, or generated frames in the videos. Now that's really cool, right? Because you are generating like videos in the domain distribution of the real world where the robot is deployed. You're still missing the action values here, and we'll get to that. But like this is already pretty cool. Now you need to have fine tuning for image to video generation, because I tried that using Sora without any fine tuning, and it doesn't work. Like the robotics data that I have here is like very out of distribution for the videos that this model was likely trained on, or even this one here. Yeah, so I think you need to have a pretty good fine tuning for image to video models, which is, I think, kind of difficult or more like a bit expensive at this stage, but maybe it becomes like very easy in the future. It might be as easy as just fine-tuning an image model, or it could even be something like the stable flow from Snap, or like this new paper from Apple, where you can control the latent vectors to actually manipulate the images or the videos without necessarily any fine tuning of the models. So, but for now, yeah, fine tuning image to video model. Now we get back to how do you generate the action values for them. So what they do here is they train a inverse dynamics model, IDM. This is basically the same like an imitation learning side. So what you do is they don't have them. Oh, yeah. Now what you do is you train a diffusion transformer which takes image t and image t plus h as an input, and it takes the teleoperated action values from the robots as output. It's like done using flow matching because of the continuous values of the robot. Once the model is trained, then they use the generated images. They use generated images like ht, xt, and t plus h, which is 16, and predict the actions, and then use these actions to train the group policy, along with the latent actions too. Once again, like to repeat, first you train an image to video model, you fine tune it on the robotic data set. Using that, NVIDIA generated around 800 hours of video data. So using 88 hours, they generated 827 hours of video data. Now you take this video data, so sequence of videos for every task, and you generate you take the real video data, you train an imitation learning based model, so IDM, not imitation learning, but it's a similar model. In this case, they use diffusion transformer with flow matching, train it to predict the action values for the teleoperated robotic data set, and then use that to predict the action values for the generated data set, that is like for the neural trajectories that are generated, and use those then to train the group policy along with the latent actions that we talked about here. So yeah, I think that this was one of the nicest things what NVIDIA did. This was one of the best trick I think I found in the paper. One of the other thing that they do is they use simulation, something called text mimic chain, but this is very nicely documented topic from NVIDIA. If you go to the website, you can find like enough information around text mimic chain. But these two were, for me, the most exciting parts: getting the action values for the human demonstrations, and then generating like completely new videos for robotic data sets, and then generating the action values for them, and then training on top of it. Like one of the questions is like, why would you generate new videos for robotic data set if you can just simulate them? One of the things is to make sure you don't have the sim to real distribution gap. And second is like some things like they talk about in the paper where they're generating videos for pouring coffee, folding laundry, folding things. So cloth or fluid, it's very hard to simulate. So, but it's relatively easy to generate for the video generation models. And that helps a lot here. All right, I think this was it for the with Groot. And let's talk about Gemini and how we can use it to do some clever things next time.